Hi, my name is Andrew McLaren. I'm going to help you understand how to solve these problems with pulleys that are massless or they don't have inertia, um, to solve the acceleration when you have one or maybe two suspended by the pulley and you're trying to figure out how that system is moving. There's a trick to this using some analogous movement and canceling out like the internal forces. So we'll go through that first with this problem, then one that's more like well, I've labeled number two, and then this third one as well. And they really do connect quite well together, but if you want to just skip ahead, you can go ahead and do that if you've got like an example problem in your homework. So in this problem, we have three masses, two of which are on a flat surface without friction, and the third one that is suspended by the pulley. These will accelerate a bit differently depending on how much mass is in different locations, but the main trick that you want to do is think about the forces acting in the x direction for what we've got for label A and B. So those have some forces acting in the x direction. And for our object, I'm going to go with object C right here. It's going to be moving in the y direction. And they're going to be analogous to if we had three different masses that are the same sort of size and they have some rope between them, but they're actually just moving side to side. So we're going to have this analogous movement. We're going to just be thinking about it as one set of forces in that x-axis. And the trick that you want to do is think about this as one object that is being pulled on in a certain direction. Now, the internal forces, aka if you think about this as like some sort of tension for that first rope or some tension in that second rope, those will have some values that you could solve for later. But because they're these internal forces, they kind of cancel out. You don't need to ask how much this larger purple object is being pulled in a certain direction. So this object C, it's got this force right here that's acting on it. So this you could think of as the force of gravity on object C, or you could think of it as some sort of force applied to this larger system. Like maybe someone's grabbed onto that last block and is pulling it. And now that is a similar sort of thing as in our pulley problem where there's a mass that's pulling that down, but that mass is not going to be pulled down for like B or C in the direction of movement. So they do have forces that are canceling out in their Y direction for A and B, but in the X direction, they've got some forces that we could solve for later in the problem once we know how this whole thing is accelerating. So if you think about this, you've got that force of GC, which is equal to its mass times acceleration of gravity. I oftentimes like to think of that as a negative number, so I don't really like writing that as g, but we've got acceleration of gravity, which is about negative 10 meters per second squared. We could go with 9.8 if we want to be more precise, but it is times this mass of object C. So if we wanted to think about that, we've got 2m naught pulling that downward. And then we can think about a larger system, this larger block, if you will. Now, if we're thinking about that in the x direction, the only thing that's really acting on that is this force applied, or about 2 m naught times g in that negative direction. So it's getting pulled with that amount of force, but for the x direction of this system, you could think of this as A plus B plus C. Their total mass is going to be 2mo plus mo plus another 2mo, so it's 5 mos or m naughts worth of mass, and that's going to be the acceleration that we're actually experiencing. So in other words, if we wanted to rearrange this, we've got that and that equal to each other. The acceleration of this system should be equal to 2 m naught over 5 m naught times the acceleration of gravity. it is going downward in this y direction, that acceleration, so it should be a negative number in that consideration when we're thinking about that going downward. And then for like mass 1 and 2, they're going to be moving to the right, so you might think of those as positive. In other words, the tension, the force of tension 2 here is going to be bigger than the force of tension 1 when we're thinking about the movement of object B. And for object A, it's only really having that force of tension 1 acting on it, so that should correspond to the acceleration that we're seeing. If we had some actual masses, we could actually solve for those forces as well. So if you want to just plug in 1 kilogram here, you could do that and look at like the sum of forces in the x direction of A, where we know that it's going to be about 2/5 of the acceleration of gravity, or its acceleration. And we know the mass of A. So let's say that A was like 2 kilograms, and that is going to be times a calculated value of about 2/5 of the acceleration of gravity. And we could, if we're doing this as like the 10 meters per second, then we could just do a little bit of simple math and even solve for that tension in that first rope. So we've got 10 times 2 divided by 5 for that acceleration value. So it's about 4 for its acceleration. And then we can times that by the 2 kilograms that we have for object A, because it was 2 times the base unit. So you could say if m naught is equal to 1 kilogram, then we could say that the sum of forces here is about 8 newtons, which is the force of the tension in that first rope. So you could solve for that, and then you could go ahead and also solve for this other force T2 in the same sort of idea. The forces on T2 right here, sum of forces in the X, let's say we're talking about B. Now you've got the force of that first tension plus the force of that second tension. And we already found this number above, but really we should think about it as a negative number for B, because that's going to the left, and going to the right usually is thought of as positive, which the acceleration is a positive number. So you could go ahead and plug that in, knowing that it weighs, let's say, 1 kilogram for its mass times the acceleration that we're experiencing, which was that 2/5 times g. So we have that 10 times 2 divided by 5. That's 4 meters per second. So we know that the net force here is about 4 newtons, positive 4 newtons, which is equal to that's 8 newtons from that first tension plus whatever we have for the second tension. So the force of the second tension is going to be, it looks like, positive 12. And we can even go so far as to doing the acceleration now for this block C. So the sum of forces for block C, it had the force of the tension 2, but it was kind of, that tension was holding it up, plus the force of gravity on C. And we have some numbers, so we should be able to have a corresponding calculation where we've got the mass of C times the acceleration that we're actually seeing here. I think that we'd said mass C was 2 m0 or 2 kilograms. And similarly to what we did before, we've got an acceleration of 4 meters per second squared. But in this regard, up and down, we have to consider that direction. And for object C, it was going downwards, so I would like to think of that as a negative acceleration. That's just how we normally think about it. And if we set it up that way, then we have this force of tension up and this force of gravity down. So we should be able to relate those. Now our calculated force of tension up was 12 newtons in a positive direction. And the force of gravity down, if we think about this as the m times g, um, we've got the 2 kilograms times -10. So we've got the of gc, which was equal to its mass times the acceleration of gravity, which is a -10, 2 kilograms, and the -10 meters per second squared. So yeah, this is going to be a -20 newtons from that gravity, and that does seem to be adding up to the -8 newtons when we put those two forces together. So we can go ahead and solve for like forces of tension, but it does depend on exactly how big our masses are. So I just use that 1 kilogram to help us see the relationship there. So in this problem, I've given us some actual masses. We will find the acceleration as well as that tension in this rope. And the best way to do this is to think about these two boxes being connected by a rope, and they're being pulled by like two opposing forces in different directions. But we're going to think about it as this larger system and not worry about that tension because it's essentially an internal force that's canceling out. I like to say it's like if you're worried about all the forces inside of you, that would be very complicated, but usually we're just looking at your motion as an object, not worrying about how much your food is pushing on your stomach or your stomach's pushing on your food. So if we look at this, we've got maybe this force of gravity on object 2. So we're going to call this object 2, and then we're going to call this object 1. And we've got this force of gravity on object 1. Now, force of gravity 2 should be 4 times as big. It's a much larger mass, so that's going to have a much larger force. If we want to keep it proportional, then we should do something where it looks about 4 times as big. So we have this larger system having these two different forces of gravity acting on it. We can do our mass times the acceleration of gravity. And in this case, how I've set this up, I'm thinking the acceleration is probably going to go to the right. This whole thing should be moving in that direction, which you can kind of see where this mass is going downward that way. So I'm going to do this as like my positive direction for our acceleration. So trying to think of that acceleration as a positive, then this acceleration or going to the right here is going to be matching positive being that way. So when we think about that force of gravity pulling on this object 2, which has 4 kilograms, you can think of that 4 kilograms times the acceleration of gravity. I'm just going to go with 10 meters per second squared. But in this case, it's going in that way. So we're going to keep it as a positive because the acceleration of gravity is pulling that downward in our picture, but to the right in our simplified diagram. Then we've got this other mass. So we can think of that as mass 1 times the acceleration of gravity. This was for mass 2. So for mass 1, it's got 1 kilogram, and the acceleration of gravity pulling it, in the negative direction in our diagram is going to be thought of as something like this. So you can see one of these is clearly a lot more than the other one. You can think of it as a -10 newtons pushing in one way versus a positive 40 newtons in the other way. So you can see that one is winning out over the other one. So if we want to think about this larger object that's analogous to this, in the x direction we have these two forces being added together but in opposite directions. We're going to keep this being a positive number because that's matching what direction we're going in, and this will be a negative number that we're adding to that as well. So when we look at those two forces together, we're getting a positive 30 newtons going to the right side. And we can also say that that is, for that sum of forces, equal to the mass total times its actual experienced acceleration. So if we have 30 newtons here, that's going to be equal to, it looks like 1 plus 4 kilograms, so 5 kilograms of mass. And we can look at what our actual acceleration value should be like that. Now I think that's going to be 6 meters per second squared in the positive direction with how we've set this up. So the acceleration is going to be at 6 meters per second squared, which could be going upward if we're thinking about it like here being positive, but it goes downward. So you could think about it as a negative 6 meters per second squared when you're looking at object 2. We just need to be careful with that. If we want to find the force of tension, what I might do is just look at object 1 real quick. And so for object 1 in the y direction, there are two forces. We have the force of the tension going up and the force of gravity on object 1 going down. So you can think of that as a negative number. You can think of that as a positive number, recognizing that the sum of forces should be positive to get that positive acceleration. So if we're thinking about mass of object 1 times the acceleration, which we also know is a positive number, that kind of matches what we've talked about so far. Object 1 was 1 kilogram, and it was accelerating up with a 6 meters per second squared rate in that positive direction. So the sum of forces for this should be 6 newtons, positive 6 newtons. And we have the force of gravity 1, which we calculated earlier in orange. So that was negative 10 newtons that we are adding to this force of tension. So I'm going to label the tension in blue here. Force of tension, which you can think of as like this force going up, or it's kind of like this force that's internal and canceling out. One of them you can think of as a positive and a negative in that internal diagram, which kind of cancel out. So if we think about this, it looks like our force of tension should be, what is that? Plus 16 newtons. So 16 minus 10 gives you 6 newtons. And we can check that also by looking at our other force diagram. Let's do that in a slightly different color. Let's do that in this light blue right here. So if we think about our sum of forces for object 2, that is equal to the force tension plus the F of G2. And we need to be careful with our acceleration here. You can either work with that acceleration being positive going down or positive being in the upward direction. I'm going to try and have like our normal convention of up being positive. And in that case, the acceleration that we're experiencing is a negative number because it's going downward. And if we're thinking about that as a negative number, the sum of forces for object 2 is a negative. Meaning this force tension, it's kind of going up, force gravity is going down. So they're kind of canceling it out, but not completely. So we do need to be a bit careful with that. For object 2, it was 4 kilograms. And that 4 kilograms was being times by this acceleration that we're actually experiencing, which was 6 meters per second squared. I'm thinking about that as a downward direction for this diagram and how I've labeled it. And then we also have this FG2, which we calculated earlier as a 40 newtons, but I'm going to think about that as a negative 40 newtons because gravity is making it go downward. So if we look at this, we've got, what is that, negative 24 newtons total. And then we've got this force tension plus the negative 40 newtons there. So it looks like the force of tension is, in this case, a positive 16 newtons. Now, I could have done this also with a slightly different way of thinking about this. If I wanted to do this as a positive, this being a negative, and that being a positive, that would be acceptable. That would kind of line up with the acceleration being a positive number if we wanted to think about it that way. So we could think about this as a positive 24 newtons being equal to the force tension plus 40 newtons, which was, that force downward. But in this instance, we're thinking of downward being a positive, and then force tension would end up being a negative 16 newtons. That kind of lines up with that kind of weird acceleration being positive, going downward way of thinking about this. So yeah, that's how you would do this problem from a couple different perspectives. But this trick is it just makes the math really easy for you to see the relationship. So this problem is a bit of a challenge because we have this force of gravity that does go straight down. For this one, I'm going to call that FG1. But this force gravity is kind of complicated for this FG2 because it is going to be broken down into components in a triangle. So if we want to think about that FG2, we've got this triangle that looks about like what we've done. Now, if we think about the X degree has kind of rotated 60 degrees, so the Y has also rotated about 60 degrees. So you can see your 60 degrees is about there in your triangle, and I've got this FG2. And then we can think about this as FG2 in its X direction and FG2 in the Y direction. This will be important because we're going to need to use some trig functions to relate the actual magnitude of these forces. So the for FG1, it's pretty straightforward. There's just that gravity down and the tension up. But for FG2, for its force diagram, you've got these components of f of g in the x and f of g in the y. And there is this tension. I'm going to label that as this kind of blue line here that we don't know exactly how big it is compared to FGX, but we have this force of the tension in the rope, which is kind of like going along here and also along here for our rope. So we are going to need to do a little bit of fancy tricks with this, but the main idea is that we've got two objects that are connected by some rope and they're getting pulled on. Maybe someone's pulling it some strength one way and someone else is pulling it with a different strength another way. So if you look at this larger system, it is going to be accelerating at a certain rate that corresponds to those two forces. So we don't need to worry about the internal force because that's not really included in a force diagram. We're just asking what's acting on this system. So we've got this FG1, which is pretty straightforward to calculate. We've got the mass of object 1 times the acceleration of gravity. So if it's 1 kilogram and it's times this acceleration of gravity, which is let's go with 10 meters per second squared. In this case, if we're doing left being negative, then this acceleration should also be thought of as a negative. So this is pulling back at like a 10 newtons in the left direction. Now in this case here, what's going in line with our triangle, what we've got here, is going to be this FGX. So we do need to find out what f of gx is. So we're going to need to do a little trig function to do that. If we go with TOA, if we're trying to find that FGX, that's really the focus. There's also a normal force acting on this object, but we're not going to worry about that so much because we're going to just assume that this is a frictionless surface, so we don't have to worry about any friction. You could do this with friction, but we're going to focus on the main trick here, and it's easier if we don't think about that. So if we've got our trig function, this is our hypotenuse for 60, this is our opposite, and this is our adjacent. So if we go with sine of theta being opposite over hypotenuse, then we've got sine of 60 degrees being equal to this FG2x over FG, and 2. We know that FG2 was equal to its mass, which I think was just 1 kilogram, times the acceleration of gravity, which we're going to go with a negative 10 meters per second squared. If we think about that in that regard, then this is a negative 10 newtons for FG2. So if FG2 is having a magnitude of 10 newtons, you could also like think about this triangle being all positive values. That's okay. We still have like the 60 degrees in that situation. Then we can do 60 degrees, sine function of that. That's about 0.8660. So if we were to get FG2x, that's about 8.6 newtons. And so if we're trying to figure out how big these two forces are, we have an 8.6 newtons going in one direction and a negative 10 going in the other direction. So in this problem, you can think of this thing as accelerating that way. So it's going down for that object 1, going up for object 2, and we can go ahead and solve for that tension and double check it. But let's first get our acceleration value. So if we wanted to think about the sum of forces in this weird combo system right here, the sum of forces is equal to the mass times the actual acceleration. And the sum of forces is these two numbers put together in terms of the negative 10 newtons plus that 8.6 newtons, or I guess we could say 8.7 if we're technically rounding this, but we're going to not worry too much about the sig figs on this. We're focusing more on the diagram. The mass total that we're moving here is 1 kilogram and 1 kilogram, so we've got 2 kilograms. And we can use that to find this acceleration. So we've got 8.6 minus 10, got a negative 1.4, or I guess negative 1.3 something if you want to go with that. 2 kilograms acceleration. So our acceleration, when we think about this way, is negative 0.7. So it's accelerating to the left for this simplified diagram that we're talking about, which kind of matches with this thing moving to the left, mass 1 dropping, mass 2 rising up. So we do have the acceleration, which is 0.7 meters per second squared. These things didn't quite cancel out, but they're close. And 60 degrees is pretty steep, so this thing is almost going down completely, but not all the way for object 2. Probably the easiest one for the force of the tension is to focus on this, because then we don't need to worry about any of that trig function stuff. So if we look at the sum of forces in object 1, you have that force of tension plus the force of gravity on object 1. We already calculated that force of gravity for object 1 might be thought of as negative 10 newtons. So that's like going downward, being negative. So that means that the magnitude of these things like that should be a negative, that should be a positive. The sum of forces should be a negative because our acceleration that we're experiencing is a negative number. So we've got negative 10 newtons for our force of gravity. And we're solving for this force tension by knowing that we have this mass of object 1, which was 1 kilogram, times its experienced acceleration of 0.7 or negative 0.7 meters per second squared as it's moving downward. So the newtons here is negative 0.7 newtons going to downward direction for the sum of forces. And you can see our force tension works out kind of like this. So it's not quite as big in magnitude as the -10 that's kind of winning out. So the force of tension is a positive number, and it's a positive 9.3 newtons. And then if you want to just challenge yourself with that trig function and checking all of those numbers, we can also put that force tension in here and see if it matches our experience to acceleration with that other diagram, similarly to how we did that for our object 1 and object 2 in the last problem.